So it seems like just about one section in every chapter is the word problem section, and 3.6 is our word problem section for this chapter. There are a few other word problems in the chapter, but this section is all word problems. There aren't any other styles of problems. And every single problem in this section I took from the brief calculus book that we have, or that we were using at least last semester. The difference between what we're going to do and what you're going to do in brief calculus, first of all, every word problem that I wrote a set of steps, A through E, to kind of hold your hand to walk you through the solutions process. In brief calculus, if you get into that class, you'll be given the problem without the hand-holding steps. And because this isn't a calculus class, we can't use calculus to solve the problems, and we're going to solve the problems using a graph that we'll steal from our graphing calculator. But when you get into brief calculus, this strategy of setting up the problems is going to be the same. And then when we get to the point where we get the solution, in calculus, you'll use calculus. For our purposes, we'll use our graphing calculator. All of the problems are geometric in nature, and it will help if you draw a picture. Every picture is a rectangle or a square, so it's not a terribly complicated picture to draw. And there's going to be a few formulas that we're going to need to know in this section. Specifically, you need to know the formula for a perimeter of a rectangle. Just draw the rectangle. Usually a rectangle has long sides and short sides. Normally we call the short sides the widths. W stands for width, and the long side the length. And we usually use P to denote the perimeter, and the formula for that is normally 2W plus 2L, or 2L plus 2W. We're just adding up the length of the four sides because there's two sides that are widths and two sides that are L's. That's why that's the formula we use, just as the sum of the lengths of the sides. We also are going to need the area formula for a rectangle. And that's just length times width. And the last thing that we need is a volume formula. I guess I'll say for a box or a cube. So well, this is going to be not pretty. I made this more like a cube with all the sides to be the same length. They don't have to be the same length. The bottom of the box we'll call the one of the directions a length. Another direction a width, just like because the bottom of the box is a rectangle, and then the distance from the bottom to the top of the box we call the height. So it's kind of like the area of the base, which is a rectangle, times how tall the box is, and the volume of a box is going to be length times width times height. So those three formulas we're going to need. Mostly we're going to need the top two formulas, and with those formulas intact. Oh, my drawing didn't make it so much. So I drew this lovely box, and there's a length. So the bottom of the box has a length and a width, and I probably should have made this the L and that the W, because this is longer, and usually you make the length longer than the width. But it doesn't matter when you're defining the sides of a rectangle or the base of a box. The W and the L are interchangeable. When you solve your problems, you'll get the same numerical answers. If you switch your W's and L's from mine, it's just that, like, my answer might say a length is 50 and a width is 30. You might say the width is 50 and the length is 30. Same numbers, giving them different names. Usually we reserve the length for the longer of the measures, but it really doesn't matter. So if as you're doing the problems, if you're working ahead of me, if if you start having your W's and L's switched, it just doesn't matter. You'll get the same numerical answers, and that's all we're worried about is the dimensions, and not so much so what you call the dimensions. If you call one dimension a length and I call it a width, as long as it's the same number, we're content with that. All right, so for every problem, I'm going to read through the problem and just draw a really crude picture that models the problem. Most of the problems are going to involve rectangles until the very end, and then those involve some boxes or cubes. So in this particular problem, we have a campground owner, and most of these problems are campground owners for whatever reason. The book that I took them from had a lot of campground problems. Anyways, he wants to enclose a rectangular field bordering a river, and he wants to find the dimensions of the field that give the largest area. So he needs to build 3 sides of a fence. So there's like a river. Should have brought my blue marker for that, but oh well. And then he's going to build a fence that has 3 sides. So it basically says he wants to enclose a rectangular field bordering a river. Then it should say there's no fence needed where the river is. That's implied when you're doing a river problem. They don't, for whatever reason, put a fence to block the river. And maybe I'll add that to the problem in a bit here when I go back to my office. So I'm needing to build 3 sides of a fence, and the sides I need to give names. I happen to draw the side parallel to the river longer, so I called it a length. If you would have drawn something like this, and you called these lengths and that width, there isn't anything wrong with that. Yeah, eventually we'll get the same numerical answers, except you might call your L a W and my W an L. I have a picture sketched and only one number in the problem. That one number I'm going to use to create a formula. And the 1,000 meters of fence, that's a linear measurement. That's not a square. That's not an area measurement. So that's going to be the perimeter of my fence. So I know that the perimeter of the fence that I'm going to make is going to use all 1,000 meters. And normally perimeter is 2W plus 2L, but for my situation here, since I'm only building 3 sides of the fence, my perimeter is going to be 1L plus 2W. So this rectangle has a perimeter and it'll eventually have an area. For what it's worth, I don't need it right yet, but this rectangle, even though I'm only building 2 sides of this rectangle, or 3 sides of this rectangle, the area of this rectangle is still length times width. The fact that there's a side that I'm not building doesn't change the area. So the big thing here is to draw a picture of what we're doing. Understand the 1,000 that it's given in the problem is 1,000 meters of fencing, and that's going to be the fence that I use for the perimeter. And this is not an area number, it's a perimeter number. So I took the 1,000 and found how it fit into the scenario. In this case, the 1,000 is going to be the perimeter of what I build, which is 1 length plus 2 widths. Having this sort of understanding of the problem, I should be ready to do the problem. The first part says write an expression for the length of the field, which means write an equation that says L equals, because L is the length. Well, I wrote an equation that said perimeter is 1,000 equals L plus 2W. It's not terribly hard to solve this for L, and that would be writing an expression for the length of the field. Just means write an equation that has L solved for, or L equal to something. And for my part A, if I subtract 2W from both sides from the equation I created for the perimeter, I get 1,000 minus 2W equals L, and that's the answer that we'd want for part A. That is an expression for the length of the field. Part B, I did already, but not already enough. Part B says write an equation for the area of the field. Well, the area is just the length times the width, but when we're dealing with our graphing calculator solution for the problem, I can't have two letters to the right of the equal sign. I only could have one letter. So I'm going to change the L to 1,000 minus 2W. So in general, the area of the field would be area equals length times width. I'm going to change the L to 1,000 minus 2W, and I'm going to write area equals 1,000 in minus 2W in a parentheses for that L, and then times W. So this formula for the area is something I'm going to use to get my answer. My goal is to find the dimensions that of the field that are going to yield the largest area. What I'm going to do now, and what I'm going to do for every problem once I get done with step B, is sketch a graph of the function that's defined. And this is going to be a little bit tricky because the window is going to be funky. So I'm going to graph y1 equals to, and I have to use x's. I can't use a's. I can't use w's. I'm going to get 1,000 minus 2x times x. What this graph is going to give me is a shape, and every point on that shape will tell me, given the width, what area I can enclose with that width. For instance, if I put 10 in for x into this equation and did parentheses 1,000 minus 2 times 10 times 10 and get 800. So when I plugged 10 in, I got 800. And what this point would say is if the width equals to 10, and I guess it's meters as our units, the area is 800 square meters. Let me just do it with another number. Let's make the width 100. If the width was 100, I can go 1,000, oops, clear parentheses, 1,000 minus 2 times 100 times 100. Because 1,000 minus 2x times x, I'm just putting in the 100 for the x. Then it says it's 80,000. So it says if the width is 100 meters, the area enclosed is 80,000 square meters, which is way better than having a width of 10 meters. So every point on the function, the graph of the function, is going to, the x-coordinate is going to be a width, the y-coordinate is going to be the corresponding area, and I want to find the value of the width that maximizes the area. Graphically, that's going to occur at a maximum point, a local maximum point for the graph. So I'm going to graph the function with a window that I can see the local maximum point, find the coordinates of the local maximum point, and that's going to be my answer. So I'm going to need to play with my window a little bit. So ultimately, I'm going to graph this function. Unfortunately, the standard window from negative 10 to 10 on the x's and negative 10 to 10 on the y's isn't going to help me see what I need to see. So I'm going to need to get a custom window that fits this problem. That's the hard part. When it comes to the test, I'll give you a window, because ultimately you're going to solve this with calculus when you get into a calculus class, and you won't need any sort of calculator to get the answer. But because we're limited, we don't know calculus yet, we're going to graph this, and I'm going to make guesses on the viewing window. First of all, I have 1,000 meters of fence, So if I take the 1,000 and divide it by 2, that means no side could be bigger than 500 meters. X stands for the width of the fence. I'm going to say my X min is 0 because I can't have a side less than 0 meters. And I'm going to make my X max 500 because I can't have a side more than 500 meters because if I had the 2 sides would use all 1,000 meters up. So those are my widths. I'm looking at widths between 0 and 500 feet because that kind of makes sense in terms of this problem. And then the Y min and the Y max, I see that I can enclose 80,000 square feet. I know I'm going to do at least 0 square feet, and I already got 80,000. I'm going to make a guess, and this just might not be a good guess. I might have to tweak my Y max, but just by looking at the size of the number I got from my sample point, which was in the tens of thousands, I'm going to make my Y max 300,000. I'm going to sketch the graph, and I hope that I see the local maximum point, which I may not. And if I don't see the local maximum point, then I'm going to tweak the Y max. I think the X's are okay. So I'm going to type the function 1,000 minus 2x times x. Hit my window button. I'm doing x from 0, x min 0, x max 500, y min 0, y max 300,000. There isn't anything right or wrong about this window. You can use a different window, and as long as you can see a maximum point, your window's okay. So now when I hit graph, I see what I need to see. I probably made my y's way higher than they needed to be, but that's completely okay. This point right here, like the points that I figured out, the point 10, 800 is probably down there. That point having a width of 10 feet and an area of 800 feet is potentially there. Maybe the other point that I figured out having a width of 100 feet and an area of 80,000 square feet might be there. This point up there, the vertex of this parabola, that's the maximum, that's the optimal point. The W and the area, the width and the area that correspond to the vertex is what I'm going to need to find. I'm going to find that by using my calculator. I know this is a maximum point. I'm going to hit the second button and then the trace key first. So I hit second and then trace. Because this is a maximum point, I go down to option 4 that says maximum. So I hit second, trace, went down to number 4, hit enter on maximum, and now my calculator says left bound. What I need to do is use my right arrow or my left arrow so that I could get the blinking cursor clearly to the left of the maximum point. My blinking cursor could be really far away from the maximum point, or it could be really close to the maximum point. The closer you get to the maximum point, probably the more efficient your calculator is going to work. But ultimately, for the first part of finding the maximum, I need to use my left arrow probably, get the blinking cursor to the left of the high point, and then hit the enter button. And once I hit the enter button, the left bound question is going to go away, and it's going to ask for a right bound. So I hit enter. My calculator puts a little arrow. It says I'm going to start looking here. Then it asks right bound. Right bound means where do you want me to stop looking? Now I'm using my right arrow, getting the blinking cursor so it's clearly to the right of the maximum point. Again, there isn't a right and a wrong place to leave this, but the closer you get your blinking cursor to the maximum point, the better your calculator is going to work. So now that I have with the right bound question, my blinking cursor to the right of the high point, I hit enter a second time. So now my calculator says I'm going to start looking here, I'm going to stop looking here. Give me where you want me to start. Make a guess at where the maximum point is. So I move as close as I can to the maximum point, hit enter again, and my calculator will tell me what it thinks the maximum is. And very often I have to round the x. My calculator doesn't do calculus, and it does something so that when it gets close enough to the maximum it stops looking. And I'm going to say this. I'm going to take this 249.9999997 and round that to 250. And it always does well in the y's. It just doesn't do so well in the x's. So the maximum point for this parabola that looks something like this, I'm going to say is the point 250, comma 125,000. And this, so what that point says is that, so that point, the point 250, comma 125,000, says when the width is 250 meters, the area is 125,000 square meters. I'll use the symbol for square meters. Because this is a maximum point, there isn't going to be a better dimension in terms of the width of the field. Because any other point is beneath this point, any other point, its area is going to be less than 125,000 square meters. So this point right here is going to give me most of my answer. So now I've sketched a graph, found the maximum of the graph, understand that the maximum tells me the width and the area that are optimal for this problem, and I'm going to answer the question. The C, find the value of W, or the width that leads to the maximum area. The width is going to be, we came out with 250 meters. I can't answer part D without doing a little bit of algebra, but I can part E. The maximum area is the 225,000 square meters. I'm going to write an M with the square to be square meters. The only thing I haven't answered, the only thing my calculator doesn't give me, is the optimum length. So I'm going to use the formula, length equals 1,000 minus 2W, in order to get the answer for part D. To get the answer for part D, I'm going to take the formula length as 1,000 minus 2W that I came up with in part A and change the W to 250, which is the optimal width. And so this is going to give me 1,000 minus 500, which is going to be 500. And the optimal length is going to be 500 meters. So for part D, the optimal length, the length of the dimensions, the length that will give the maximum area is 500 meters. That's everything that needed to be answered. Ultimately, it's only part A and part B that I have to be pretty clever to get. Part C, D, and E, I'll either get from my calculator or I'll get from the formula that I created in part A. Okay, I have to make a note to myself to say something. We only need to build 3 sides. And I'll type that in. So 4 is a similar problem. It says no fencing is needed along the river again. In fact, it's the same problem, which means I should change the numbers. How about this? A campground owner has 2,000 meters of fencing. He wants to enclose a rectangular field bordering a river with no fencing needed along the river. That's what I needed to change the last part to. I just didn't have that in there. And let W represent the width of the field. So this problem is a carbon, it's essentially exactly the same problem as the last problem. So I'm going to draw a picture. First of all, I'm building a rectangular region, and I'm only building 3 sides of fence. Generally, I call the sides perpendicular to the river the width, and the side parallel to the river the length. I know that the perimeter that I'm going to build, I'm building 1 length and 2 widths, and I know the area is still length times width. Because the number that's given in the problem that I tweaked is the perimeter, I'm going to plug 2,000 in for the P. And so my perimeter formula, because that 2,000 represents the perimeter, is going to be 2,000 plus 2,000 equals L plus 2W. Having that understanding of the problem, I can go and do the questions. First question says write an expression for the length of the field. I'm going to take this 2000 equals L plus 2W, solve it for L by minusing 2W from both sides. When I do that, I get 1000 minus 2W equals to L. That's the expression for the length of the field. The area of the rectangle was generally length times width, but because the calculator can't handle 2 letters to the right of the equal sign, I'm going to change the L to 1000 minus 2W again. So I'm going to get A equals, should be 2000. I don't know why I made it 1000. That should be 2000. Should be 2000 minus 2W times W. Just changing that L right there to 2000 minus 2W. Now I'm going to graph it. It's going to be easy to graph in terms of I can just hit my y equals button. It's only one number different from the last problem. If I kept the window the same, I think I'll miss the maximum. So my goal is to be able to sketch a graph and to see the maximum point. Because I have twice as much fence, I don't think the window is going to work that I have. So I'm going to change the window. I'm going to double the x and double the area because I've doubled the fence, amount of fence. So I'm going to change my x max to 1000. And I'm going to change the area, well, to 600,000. I was way too high in the last problem. Maybe not make it not quite double. Maybe I made 500,000. Again, there isn't a right and a wrong window. The window that you get that shows the maximum is, that's all I need to do is get the maximum in my window. And if I'm clever at the beginning, then when I hit my graph, I see the maximum. If I'm not, then I have to struggle a little bit. And maybe when the problems get, sometimes it's harder for me to guess the window. And that's probably going to be on the next problem. And you'll see me struggle a little bit to get the right window. But let me hit graph here and see if I can see. Oh, yes, I can see the maximum. Maybe let me make the y max a little bit harder so you can see it better. But that's adequate. If I changed my window and made this y max actually the full 600,000, then it's maybe more clear where the maximum is. And so now I'm in calculator mode. I'm going to find the maximum point by hitting the second button and then the trace key, going down to option 4 that says maximum. I hit enter. I use my cursor to trace to the left of the high point, or the left of the maximum, and then hit enter. Then I use my right cursor, trace to the right of the top, the maximum, and hit enter. And then get as close as I can to the maximum and hit enter. And my calculator will give me something, and that 499.9999, I'm going to round to 500, and then 500,000. So the maximum point, the local maximum that I generated on my calculator, that you can use calculus to find. Actually, there's algebra that can be used to find this too, because it's just a parabola and we know how to find the vertex of a parabola. So the maximum point is 500 comma 500,000, and the x coordinate of the maximum point is the optimal width. So the value of the width that leads to the maximum area is this 500. My units are in meters, so I'm going to write meters. The maximum area is the 500,000. My units are in meters, area are square units, so I'm going to write 500,000 meters squared. The last thing I need to do is get a value for L. I'm going to use the formula L equals to 2000 minus 2W, and into that formula I'm going to plug 500 because the optimal width is 500. So I get 2000 minus 1000, which is 1000. So the optimal length is going to be 1000 meters. if I didn't have the bordering a river part of this problem, then I would have to build 4 sides of a fence, and my beginning would have this. It would have 2,000 equal to 2L plus 2W. So if this problem didn't have the river, then my initial equation would be this. Solving this for L for what it's worth, I just divide everything by 2. I'd get 1,000 equal to L plus W. Then I'd get 1,000 minus W equal to L. So the fact that I'm giving you the river, it's saving you a little bit of algebra. It makes it easier to solve for L. If I didn't give you the river and ask the same question, the difference in your problem is going to be the perimeter equation is going to be different because you're building 2 lengths. Solving for L is going to be a little more complicated, but ultimately the problem's the same problem. Once you get your equation solved for L, you plug that into the area formula and then you graph. All right, 6 and 8 are totally brief calculus problems because they deal with money. There's lots of figures in here, and it tells me, just like the first 2 problems, that I'm building a fence, but in this case I've got way more information. First of all, I'm told how much area the fence needs to enclose, and that's 20,000 square feet. I'm not told the perimeter of the fence, but I'm told costs, and it says, for whatever reason, the different sides, the north and south sides, cost $2 per foot, and I said call those sides length, and the other 2 sides cost $4 per feet to build, and I said call these sides width. Follow these steps to find the cost of the least expensive fence. If you didn't watch me do it, it would be really impressive to get the answer by yourself. I would doubt, if I was in your position, having never seen this before, that I would have any idea of what to do. So best thing I could do for any of these problems is draw a picture. So I'm drawing a rectangle, and I'm building 4 sides of a rectangle. So I'm building fence. I'm building 2 widths and 2 lengths in this case. I don't have any sides that are river bound. In the first 2 problems, the first equation I came up with was a perimeter equation. That's because the only number that I had was the amount of fence that I had to be used to build the perimeter. This equation doesn't tell me how much fence I have. It tells me the area that I need to enclose. And a perimeter equation isn't going to be helpful because the number in the first sentence represents an area. The first equation I'm going to need is an area equation. Ultimately, for all these problems, I need 2 equations. A starter equation and then the equation to be optimized. The starter equation is going to use the amount of fence that we have. So in the first 2 problems, the amount of fence I had was, I knew the amount of fence I had, so I made a perimeter equation. This, I know the area that I want to enclose, so I'm going to start off making an area equation. And so the area of the rectangle that I drew is length times width. And I'm going to change the area to 20,000. So the area formula for this is 20,000 equals length times width. I've only dealt with the first sentence. I haven't dealt anything with the cost. So I should probably start talking about the cost. It says, as I read this problem, it says the fencing material costs $2 per foot for the sides facing north and south. I think these are north and south, and I call these the length. So this side and this side cost $2 per foot, and this side and this side costs $4 per foot. My goal is to minimize the cost. And if I want to minimize costs, I need a cost equation. In the first 2 problems, I wanted to maximize area. So I came up with an area equation, graphed it to maximize it. And this problem, I want to minimize cost, so I'm going to need a cost equation. I'm going to write C for cost. And the cost of my fence is going to be, I'm going to add up the cost of each side. And the cost of a side is the cost, the dollar per foot times the length of the side. So the costs are going to be the cost of the top side, which is $2 times its length, plus the cost of the east side, which is $4 times its length, which I call a width, plus the cost of the south side, plus the cost of the west side. The cost to build my 4 sides is good. If I add the 2 L's up and the 4 W's up, it's going to be 4L plus 8W. That's everything I need for this problem. I might have to tweak some things a little bit, but this is all the information in the problem, organized well enough that with a little more effort, I'll be able to answer the question. So I didn't come up with a perimeter equation because I don't know how much fence I have. I always need 2 equations, and the number in the first sentence, because it's an area equation, my first equation was an area. My goal is to minimize the cost, so I needed a cost equation as well. In the last problems, my goal was to maximize area, so I needed an area equation. I knew how much linear fence I had, so I made a perimeter equation. So let me transfer these 2 things to the front here. I know that I have 2,000, 20,000 is the length times the width of this rectangle, and I know that the cost is 4L plus 8W. I'm trying to find the length and the width that's going to give me the very lowest cost. First, now I'm ready to answer my questions. First question says find an equation for the length of the field. I find that equation by just taking the first equation and dividing both sides by W. When I do that, I get 20,000 over W equal to L. Now it says write an equation for the cost of the field. I'm going to write an equation for the cost of the field, which I already have, but I'm going to change that L into 20,000 over W. So I'm going to write cost equals 4 times 20,000 over W plus 8W. I'm going to multiply that 4 and 20,000 and get 80,000. So my cost is going to be 80,000 over W plus 8W. When I sketch a graph, every point on the graph is going to be this. It's going to be the width and the cost associated with building a fence that has that width. My goal is to find the width that leads to the lowest cost. That being the case, I'm going to try to find a minimum point as opposed to a maximum point. So I'm going to graph this as a y1. So I'm going to, all these problems I'm going to graph. My y1 is going to be 80,000 over W plus 8W. And these windows for me are just not in that obvious. First of all, the X-min and the X-max has to do with the width of the field. And generally, I kind of eyeball the area and square root it. And that's usually what I make my X-max. So I'm going to go something clear here. And again, I'll give you these values so you don't have to be so clever. So second square root of 20,000. So I might make my width like 150. And then I'm dealing with the costs of building a fence. The cost hopefully isn't going to be millions of dollars. I'm going to maybe make my, so for this, I'm going to go X-min 0. My width can't be less than 0. X-max, and I'm going to make it into 150, which was kind of the square root of the area, rounded a little bit. And again, this could not be, they might not be perfect. My y-min is generally 0 again because my cost isn't going to be less than 0. And my y-max needs to be a reasonable number, and the cost of building a fence that's 150 feet long, that's 600 feet of fence at $3 a foot, $4 a foot, 624,000. I'm going to make this like $25,000. And what I did is I just guesstimated if each of the sides were 150, that would be 600 feet in perimeter, and the most expensive side is $4. 600 times 4 is 24,000, so I made 25,000. Hopefully, this window, I can see a low point in it. And again, I'll give you the window so you don't need to create the window, because that's ultimately more than I'd expect you to do. And ultimately, when you're solving these problems for reals, doing math to solve the problems and not using your calculator to solve the problems, you're going to be doing that math with calculus. So I entered the function that I needed to enter, 80,000 over x plus 8x. Now I'm going to hit my window, and I'm making 0 to 150 for the x's, and then 0 to 25,000 for the y's. And I would suspect, as you're doing the odd problems in this section, if you use the same windows that I use for the even problems, the window should work just fine. So when I hit my graph, it's maybe not painfully obvious that this is a minimum. Let me make the window go a lot further out. I don't know if I hit the far enough out. Let me change the x max, because to me it's not clear what the bottom is. I'm going to change the x max. I'm going to go way out. I'm going to go to 500. And then, again, if you use this window probably to do number 7, it'd probably be a good window if this actually works. Now I can see. I get a little Nike swoosh here. Somewhere's in here, the minimum that I'm trying to find is there, because the graph goes down and then it starts working its way back up. The minimum occurs somewhere around there, and I'm going to just try to find it on my calculator. So I'm going to go second in calc. So once I have a reasonable graph and I know where the minimum or maximum is, I hit second in calc. In this case, I'm looking for a low part or a minimum, so I go down and select minimum. And I'm going to use my cursor, and I can't see anything because the graph is too low, which is not good. I need to get my cursor flashing, and it needs to be clearly to the left of the minimum. So I got it way away from this, so I can see that's clearly not at the bottom. I'm going to hit enter, and I'm going to use my right arrow and get my cursor so it's clearly to the right of the minimum, which means I'm going to get it out of the words. So the minimum is clearly to, this is past the minimum, and then I hit enter, and then I get, somewhere's in this mess of writing, and hit enter a third time, and my calculator will tell me the minimum is, and I'm going to round that 99.9999 to 100. I'll say 100 comma 1600 only for the cost. That is surprising. Y equals, surprised I was off that much. So second calc, let me do this minimum again. So it was 100 comma 1600. So the minimum point that I got was 100 comma 1600. So that my window was really bizarre in some sense. It went way too high. So let me answer the questions and then talk about if that my calculator is right and I was dumb. First of all, the value of W that leads to the minimum cost, the width, the optimal width that leads to the minimum cost is going to be 100, and it's going to just be 100 feet. The minimum cost is going to be $1,600, which is nice and cheap. And I want to find the length. The length I get by taking 20,000 over W. So the length is going to be 20,000 over W, which is 100. And to do that, I'm going to cancel the 2 zeros and get 200. So the length is going to be 200 feet. So that's all the answers. And let me show you that the cost actually works out. If I plug into my cost formula 200 for the length and 100 for the width, I get cost is 4 times 200. 4 times 200 is $800, plus 8 times 100. 8 times 100 is $800, so the cost is $1,600. So when I was thinking about making my window, when I made the Y max 25,000, that was obscenely high. I did something bad in my head. I should have probably did 2,500. Would have made a much better graph than I did. So if the window on this was set at 0 to 500 and 0 to 2,500 as opposed to 25,000, it'll look so much better. I would have seen the minimum so much nicer than what I did. And if I did second, calc, minimum. So having a good window is really beneficial in terms of it just makes your life a lot easier. But because I was dumb and did math in my head that didn't work so well, I didn't see the minimum as clearly as I could have saw it with a better window. Still get the same answer, 100 and 1,600, but that window just smokes my other window. So even though I was able to get the answer because my calculator could make up for my shortcomings, I didn't make it as easy as I could have made it. So the viewing window, it does make a big deal. And if you don't get a good viewing window, then you won't be able to answer the question. 8's another money problem. It's going to set up the same way, except I get a little reprieve here. I'm building a fence to enclose 10,000 square meters. One of the sides has an existing fence, just like in a river. So here, this is the existing fence. And I need to build a fence, not as long as the existing fence, but needs to enclose 10,000 square meters. So I'm going to build 3 sides of a fence. I'm going to call again 2 of the sides widths, 1 of the side lengths. And I know the area that I need to enclose. The area of this region is just length times width. And I know the area that I need to enclose is 10,000 square meters. So I'm going to make the equation 10,000 equals the length times the width. My goal is to minimize cost. So I need to come up with a cost equation. As I read through, it says material for the fence costs $5 per meter for the 2 ends and $2 for the part across the existing fence. So this side is going to be 5, this side is going to be 5, this side is going to be 2. I didn't carry the decimals, they weren't necessary. So the cost, which I'll write as C, is going to be the cost of the 3 sides that I'm building, which is a 5W plus a 2L plus a 5W. So my cost is going to be 10W plus 2L. That's everything I need in terms of a sketch. So I knew that I've needed to come up with an area equation and a cost equation. The first sentence gave me a figure that had to do with area, so I needed an area equation. My goal was to minimize cost, so I needed a cost equation. I have my area equation, I have my cost equation. I carry those forward to the page here. So what I have is the area, 10,000 equals length times width, and the cost equals 10W plus 2L. Now I'm going to answer the questions. It'll take me to my answer. First thing, write an equation for the length of the field. To write an equation for the length of the field, I need to take this equation, divide it by W. If you divide it by W, you get 10,000 over W equals L, which I'll write L equals 10,000 over W. Now I need an equation for the cost. I have an equation for the cost, but not the one that I'm going to use. On my calculator, I'm going to go 10,000 cost equals 10 times, and then I'm going to put 10,000 over W. 10,000, that's messed up. I'm going to go cost equals 10W plus 2 times 10,000 over W, changing the L to 10,000 over W. I'm going to multiply that 2 times 10,000 and get 20,000. So my cost equation is going to be 10W plus 20,000 over W. That's the equation I'm going to graph. I'm going to leave my window where it's at right now because it's another cost problem. So this window of 0 to 500 and 0 to 2500, I'm going to leave that window. If I see the minimum clearly, then I'm not going to tweak it. If when I graph it, I don't see an obvious low point, then I'm going to tweak the window. So I'm going to graph this function, 10w plus 20,000 over w, and same deal here, I have to use x's, so 10x plus 20,000 over x. Hit my graph button. Oh, and that window is still good enough. So now I'm going to find the minimum, and the minimum is going to contain the optimal width and the cost. So I go second calc, go down to number 3 that says minimum. I trace way over, my cursor was off the screen. I traced so I get clearly to the left of the low point, but kind of close to the low point, and hit enter. And then traced till I get clearly to the right of the low point and hit enter, and then get as close as I can to the end point and then hit enter. And a lot of times I have to round my x's. So I'm going to say, ooh, this is so far off that my answer, it comes out to a string of 9s, I'm going to round it. This is a decimal answer. It's okay to have decimal answers. In calculus, they'll come up all the time. I'm going to say the optimal width is 44.72 feet. I'm not going to round 0.72 to 45. So this is just an unfortunate answer that can come up when you're dealing with semi-realistic problems. It could be that you're not building a perfect, well, in this case, meter. So my width is going to be 44.72 meters. And I should probably add round to 2 decimals in my instructions. All right, round to 2 decimals as needed. And the cost is going to be also rounded to 2 decimals, $894. I'm going to round it to 43 cents. So the vertex that I came up with was this, 44.72 comma 894.43, and that is too far off for me to round it to 45. So if this was 44.9999, yes, I'd live with that. My calculators need to round that a little bit, but it's never going to be that far off. So I'm going to leave this as a decimal form and say the optimal width is 44.72, and then the units are going to be in meters because the units given are in meters. The minimum cost is going to be $894.43, and then the value of L I need to plug into this formula. I'll get L is 1,000 or 10,000 over, should be 20,000 here. When I wrote this should be 20,000 over W, because I did 2 times 10,000 and got, oh, I guess, I'm sorry, it's okay. It is 10,000 over. It's just in the formula it came out to be, when I multiplied it by 2, and there it gave me the 20,000. So 10,000 over this 44.72 is correct, because this formula right there, I didn't have an error. So now I'm going to second and quit and do 10,000 divided by 44.72. I'm going to round to 2 decimals again. I'm going to say it's 223.61 meters. I think even on the review there's a problem that comes out to have a decimal. So when I'm making these problems up that don't even start with decimals, they can easily run into decimal answers. Not so much on the first problems where I give you the perimeter and ask you to maximize the area. Those problems I can make up pretty easily to make them work nice. But the cost problems, it's really easy for the cost problems to have decimal answers. And so as you're doing the homework, if you get a decimal answer, we'll just round to 2 decimal places so we can be consistent. The last few problems have to do with making boxes. And these are really common again in a brief calculus class. So you might see these again, and it's nice to just, at least been exposed to the setting up of the problem, because the setting up for the problem is really the hard part. The calculus that's going to be involved in solving the problems isn't that complicated. So if when you get to calculus, you start to see these fence problems and box problems, if you dig your notes out, the getting them set up is going to be the same. It's just after we get the equation that we need to optimize, then you need calculus. You can get the answer with your calculator, but your teacher's not going to accept it. So problem 10 basically says this. We have a square piece of cardboard. If I should draw a square. So this is a piece of cardboard that's 12 inches on a side. So this is what we're given. So this is 12 inches by 12 inches. So it's a perfectly square piece of cardboard. And what we're going to do is we're going to cut little X by X notches from these sides and throw those away. So what we're going to have left after we do that cutting is this. Well, I can draw that, but wish I could actually draw, but unfortunately my reality is that I can't draw. So this is what we have left after cutting. And this dimension right here is an X, that dimension is an X, this dimension is an X. Those are all X's. These dimensions that are left over, these dimensions were 12 inches. We took 2 X's away. This length from here to right here is going to be 12 minus 2X. Similarly, this length from right here to right here, even though it doesn't look like it's the same length, it's supposed to be the same. It's just that my drawing bites. This is also a 12 minus 2X. And this looks less like it. These are all supposed to be the same side. And then what we're going to do is we're going to crease this here, crease this here, crease this here, crease this here, fold up the sides and make a box. So we're just going to take these, fold them up, and the dimensions of the box, these sides are going to be the bottoms, the X is going to be the height. So when we fold this up and make a box, the box dimensions, so this side right here I'm going to call maybe like a width of the base. This right here I'm going to call the length of the base. And these X's are going to wind up being the height, because the box is going to be folded up. The 12 minus 2X's are going to be on the bottom, and the X's are going to be the height. So for this particular box that we're constructing, the length of the bottom of the box and the width of the bottom of the box are going to be the same, because I'm starting with a square and cutting out the same sides. And the height of the box is going to be the X. One of the very first things I said is that we need some formulas, and the formula that's going to be appropriate here is the volume of the box. The volume is length times width times height. I'm going to create a volume formula for my box. My volume in general is length times width times height. For this particular box, the volume is going to be the length, 12 minus 2X, times the width, 12 minus 2X, times the height, which is X, which I can write as volume equals 12 minus 2X quantity squared times X. That's everything that I'm going to need for this problem, believe it or not. These problems, in some sense, are easier than the rectangle problems that are fence problems, because I won't need to get more than one equation. In the fence problems, every one of those problems needed 2 equations. In these making a box problem, I only need 1 equation. So let me just transfer this information to this front sheet. So I have a length of the box that I'm going to construct is 12 minus 2X. And I have to decide what the X is to give me the most volume. So it said sketch a diagram to model the problem. That's really probably not as good as it could be, but it is what it is. That's a diagram that models the problem. Write an equation for the volume of the box. So I've sketched a diagram. Volume equals 12 minus 2x squared times x. And then it says graph the volume function using your calculator and find the value of x that makes the volume the largest. So when I go to sketch a graph, every point on the graph is going to be it's going to give me the height of the box or the value, the size of the notch I should cut out, and the volume I'd get by cutting that size out. For instance, if I put 2 into the formula, if I did 12 minus 2 times 2 squared times 2, plugging in 2 for all those x's, I'd get 12 minus 4, which is 8, squared times 2. This is 64 times 2, which is 128. So if I plug in 2 and I get 128, this says if I cut out a 2-inch notch, the volume of the box is 128 cubic inches. So if a 2-inch square cutout gives a volume of 128 cubic inches. So every point on the graph is the x coordinate is the size of the little notch that you cut out. The y coordinate is the volume. My goal is to get the maximum volume, so I need to find a maximum point. I'm going to graph this function. I know that the x can't be bigger than 6 because if I cut out 6 inches, I only have 12 inches to work with. So I'm going to graph this function. I can't make a notch less than 0, and I can't make a notch bigger than 6 because that's more than half the size. My y-min, I can't have a volume less than 0, and because I did this cheater point and got like 128 for the volume, I'm going to make my volume maybe like 400, thinking I can't get much more better than that. Just this gives me an idea that I needed to be in the hundreds at least rather than in the tens of thousands. So I'm going to graph this function, use that window, try to find the maximum point. The x coordinate of the maximum point is the size of the cut that's going to give the maximum volume. The y coordinate's the maximum volume. It doesn't even ask me to find the length, the width, and the height. It just asks me to find the x. And so it's much less demanding of me. All it wants is the x coordinate of the maximum point. So I'm going to graph this function, which is 12 minus 2x parentheses squared times x, and hit my window to be 0 to 6 on the x-min x-max, 0 to 400 on the y-min y-max. Hit my graph. Hopefully I see a maximum. And I certainly do see a maximum, which is beautiful. Now I'm just going to find the maximum by going second calc, going over to option 4 that says maximum, trace to the left of the high point, and hit enter, trace to the right of the high point, and hit enter, and then get as close as I can to the high point, and hit enter, and then I might have to round this if it doesn't do nicely. This 1.999979, I feel comfortable in rounding that to 2. So if it has 4 9s or 5 9s, that I'll round up. But if it's not with a string of 9s, I'm not going to round it. So the optimal vertex is 2, 128. Morning. And that coincidentally was the point that I already found. So I'm going to say exactly it. The optimal notch that I need to cut out is a 2-inch, and that was just a dumb guess that I got the actual right answer by just guessing. So the whole answer that I need is the square that you need to cut out. Is 2 inches by 2 inches. It doesn't say what's the volume, but it wouldn't be wrong to say the volume is 128 cubic inches, and it doesn't ask for the length or the width. But if I plugged 2 into this formula and did 12 minus 2 times 2, it'd be 12 minus 4, which is 8. This box would be 8 inches by 8 inches by 2 inches. Doesn't want any of that. The only thing that's asked for is the size of the square to be cut out. But if you gave me more, you said the box is going to be 8 by 8 on the base and I have a height of 2 and the volume is going to be 128 cubic inches, that would be completely fine. I won't take any points off for giving more correct information than you're required to give, but it only asks, the question only asks for the value of x that makes the volume the largest. So I don't need to say the corresponding volume. I don't need to say the width and the length of the region either. 12 is exactly the same problem, except I changed the dimensions of the box, and I changed it from cardboard to metal, but that absolutely doesn't matter. So in 12, I'm going to make a box. I'm starting off with a square base, so it'd be nice if this actually looks square. This is my diagram. It starts off to be 30 inches by 30 inches, and exactly the same. I'm cutting out squares. Those are all supposed to be squares and not something that looks unsquare-like. What I'm left with when I do the cutting, is that, and this side right here, as well as all of the sides, when I cut these x's out, have dimensions of 30 minus 2x. They were 30, I took 2 x's away. This one I'm going to call maybe a length, a width, and then the heights are going to be the x's that I cut out. And I can't draw this box folded, but I'm going to fold it along those sides again. I'm going to take this and make it into a box. I'm going to fold up the sides. So in this particular one, the base, the length, L-E-N-G-T-H, is going to be 30 minus 2x. The width, because the base is square, is going to be the same as the length. And the height of the box is the length of the notch. So the volume is going to be length times width times height, which is 30 minus 2x times 30 minus 2x times x, which I'm going to write as 30 minus 2x squared times x. So this is the diagram. It's the same diagram with just 30 replaced, the 12 replaced by a 30. So sketch a diagram, did that already. An equation for the volume. Volume is 30 minus 2x quantity squared times x. I'm going to sketch a graph. I say round to 2 decimal places, which makes me think I'm going to get a decimal answer here. So hit y equals. So easy just to change the 12 to a 30. Everything else in the equation is the same, so I didn't even need to clear out the equation. I just typed over the equation. I'm going to leave the window the same. If I don't see a maximum, I'm going to change my y max. And, well, take that back. I'm not going to leave the window the same because the x max should be half of the square. The last time I made the x max 6 because half of 12 was 6. Here I'm going to make the x max 15 because half of 30 is 15. I'm going to hit graph. If I don't see the maximum point, it's the y max that's going to need to be made bigger. So I hit my graph button, and I barely, so I can see the graph goes way, way up. My y max needs to be tweaked way higher. So I'm going to hit my window button. I'm going to tack on a 0 to this y max, make it up to 4,000. It might not be the best window, but as long as I can see the maximum, there isn't a right and a wrong window. Better windows make it easier to find maximums and minimums, but this window is good enough. I can clearly see the maximum. There are definitely other windows that would have worked. So now I'm going to go second, calc, go down to number 4 that says maximum, trace to the left of the high point or at the left of the maximum and hit enter, trace to the right of the maximum and hit enter, and then get as close as I can to the maximum. And this one hinted at me I'm going to need to round, but I don't. This 4.9999, I feel comfortable rounding that to 5. The vertex is 5 comma 2000, so I don't need that in there. Needed it for another problem that I didn't have it. So the vertex being 5 comma 2000, it says if I cut out a notch that's 5 inches by 5 inches, I'm going to get a volume of 2,000 cubic inches, and that's the most volume I could get. So the answer is x should equal 5 inches, or you could say you could cut out a square that's 5 inches by 5 inches. That's all that's asked for. If you said this, the volume is 2,000 cubic inches, that would be fine. And if you plugged a 5 into this and did 30 minus 2 times 5, which is 20, and you said the length is 20 inches, the width is 20 inches, and the height is 5 inches, that's well more than it's asked for, but it's all correct, so it's okay. So the questions about the box questions don't ask for near as much in your answer as the rectangle questions, but it's completely okay to give me the extra stuff. It's not incorrect. You're giving me correct stuff that's not asked for. I'm completely content with that. I think the review doesn't have the box problem, making a box problem for what it's worth. I think all the problems on the review that come from this section are just the rectangle, 2 dimensions, one with cost, one with a river maybe. So hopefully this wasn't the worst exposure to word problems. Like I said, these problems are absolutely guaranteed to come up if you take calculus, so they're really important to get comfortable with. And up to getting the equation, that's going to be 100% the same. But instead of solving the problem via graphing, you're going to solve the problems via calculus, which makes the problems a calculus problem, and it makes them a little bit harder. But if you have this part perfected, if you understand the setting up the problems, you'll be way ahead in calculus than if you don't understand the setting up, because trying to understand the setting up and the calculus simultaneously makes the problems a little bit harder. So these would be really good problems to really spend your time with, so that when you get into a higher class, that transition goes better.